Hi everybody, good to see so many people joining. I can see that most of the registered people have joined now, so let's get started. Welcome to this webinar about TSN in Aviation, Aerospace and Defence. I'm Schjøtler Sørensen. I'm Product Manager at Comcores with focus on Ethernet and TSN. During this webinar, I'll give you an overview of TSN and how it can apply in Aviation, Aerospace and Defence. The agenda for today consists of 3 parts. First, I'll give a generic introduction to time-sensitive networking. Then we'll go over to talk about TSN in Aviation, Aerospace and Defence. And here I will go through some value propositions and use cases for TSN in these industries. In the third part, I'll go quickly over the TSN portfolio that Comcores is currently carrying. If you have any questions during the presentation, please post them in the chat and we will try to answer as many as possible in written. And there will also be some time for answering some of them verbally in the end of this webinar. The first part of the webinar is an introduction to time-sensitive networking in general. The TSN standards are extensions to IEEE 802.1 and 802.3 Ethernet standards. TSN consists of multiple different standards. The new standard enable real-time synchronization and deterministic low latency and jitter optimized data transmission. It enabled the use of standard Ethernet components for specialized solutions. It enabled centralized network control to manage quality of service. And it enabled convergence of Ethernet network to reduce cost and maintenance effort. These advantages are applicable in multiple different markets and industries. And since the different industries have different requirements, work is ongoing to establish profiles that describe how TSN shall be used in each specific industry. Each profile defines specific configurations and sets of parameters for optimum use and standardization in a specific industry. This includes, for instance, topics like the timing constraints, priority levels, network topology, and communication requirements. Currently, 6 different profiles exist, and as seen in the right side of this slide. The first one listed here is the 802.1 DP, which is the TSN profile for aerospace onboard Ethernet communications. This is the one that we will be focusing on today. Apart from that, we have a profile for industrial automation. There's a profile for automotive, a profile for front haul, and a profile for service provider networks. And then finally, we have a profile for audio-video bridging, which is actually where it all originated, and this is where the first thoughts about TSN occurred. It should be mentioned that TSN is not only meant to be used in these 6 industries. Other industries are also investigating the advantages of TSN and how to use them in their industry. The features within TSN can be divided into 4 key areas, which are time synchronization, latency, resource management, and reliability. I will not go through all the features here, but will present some of the most important ones. Within time synchronization, these features ensure synchronization and common time perception on the network. In general, it's based on the IEEE 1588 standard, which describes how nodes can synchronize their local time of day and maintain accurate clock synchronization as low as a few nanoseconds. The 802.1 AS standard includes selected options from 1588 and eliminates several variants to improve interoperability. It also includes support for multiple clocks and redundancy clocks. Within the latency area, that's another important area for TSN. These features ensure bounded latency through the network for high priority traffic. And let me quickly go through some of the most important ones. We have the 802.1 QBV time-aware scheduler, which defines how to use dedicated time slots for different traffic priorities. All nodes must agree on these time slots, and clock sync is therefore required. This feature has a fairly inefficient bandwidth usage, since the time slots are reserved for specific types of traffic, even though there is no traffic of that kind at that point in time. But the feature does ensure low latency for the high priority traffic due to the availability of the reserved time slots. 802.1 QBU describes how higher priority frames can interrupt the transmission of lower priority frames. That means that the lower priority frames will be fragmented into pieces. The fragmented frames are then reassembled at the receiving end. This also improves the latency of high priority traffic since this high priority traffic gets through the network before the transmission of the lower priority traffic has completed. The 802.1 QAV, the credit-based shaper, defines how each queue builds up credit over time and how traffic from a specific queue can only be sent with positive credit. This spaces out the frames, reduces the traffic bursts, and ensures delivery of high priority frames over best effort traffic, which reduces, again, latency for these high priority frames. If we then move into the resource management area, this includes features that are used to manage the TSN network. The 802.1 QAT stream reservation protocol describes this protocol, which enables devices to request and reserve network bandwidth to ensure sufficient capacity for real-time or critical data streams. The 802.1 QCC standards defines management interfaces and protocols for TSN networks to set up the switches and other devices in the network. The standard includes both centralized, decentralized, and hybrid models, which can be used depending on the network administrator preferences. The 802.1 AB standard describes a protocol that can be used to discover the topology of the network, and that means that a given device can use this protocol to find out which other devices are on the network. This is called the link layer discovery protocol. The final area is reliability. This includes features that enhances the network reliability and reduces the risk of communication failures. The 802.1 CB frame replication and elimination feature helps guarantee delivery even with a defect network path. The standard describes how to duplicate each packet at the transmitter and ensure that the copies follow separate paths through the network. This increases the likelihood of a packet coming through the network, even if one of the paths is defect. This minimizes issues with, for instance, broken wires and loose connections. This feature is also quite bandwidth expensive, since bandwidth is used to send multiple copies across the network. The 802.1 QCI improves the network robustness and prevents traffic overload. It does this by making sure that the traffic complies with certain rules before it's distributed to the network. And thereby it protects the network from wrong traffic or traffic with errors in it. So this is a long list of TSN features, and it's important to mention that TSN network do not necessarily have to have all the features enabled. In aerospace, the color coding here shows the most important features, which are also some of the ones that I just talked about. We then get to the next part of the agenda, which is TSN in aviation, aerospace, and defense. Since low latency and synchronization is crucial for safety and performance in an aircraft, TSN has great potential in these industries. The legacy profiles that are currently in use do not provide the same advantages. Some of them, for instance the one mentioned here, have not evolved to support the increasing need for more bandwidth due to the higher amount of data being generated. This increasing data amount comes partly from the fact that more sensors and devices are being used, but also from the fact that each sensor and device on the network is requiring more bandwidth for more data capture and more processing. The A-Ring 664 protocol is based on Ethernet and does support a high bandwidth, but it does not inherently include a common time concept and can therefore not immediately be used for time-critical messages. As mentioned, the 802.1 DP profile defines how TSN features can be configured for the aerospace area. This profile is being developed as a joint project between IEEE and SAE Avionics Network. Many of the aerospace of partners from the aerospace industry are also involved, and it's being aligned with their expectations. What the profile does is that it's narrowing down the configuration and feature options to ensure interoperability. The profile actually consists of both a synchronous and an asynchronous profile. The synchronous is the one that needs to be used for the time-critical data. These applications are currently supported by the non-Ethernet protocols in use. The asynchronous profile is intended for traffic which are not time-critical. This profile does not support time synchronization or the TSN features that are dependent on time synchronization. These applications are currently covered by the Ethernet networks in the aerospace industry. The work of this profile, of course, has focus on the safety-critical nature of aerospace while defining the features. The status of the profile is that a review of draft 1.0 from July this year is currently in progress, and the intention is to release the profile next year in 2024. Even though the title says aerospace, it covers a lot of different application areas, which are seen here in the bottom of the slide. So both commercial aircrafts, fixed-wing military aircraft, helicopters, military helicopters, drones, and satellites. This slide shows some of the important value proposition that TSN brings to aerospace, aviation, and defense. It's important to mention that safety and risk control are both hygiene factors in these industries and therefore not mentioned as value propositions, even though TSN certainly addresses these areas. The value propositions here are the areas where TSN distinguishes from the legacy protocols. The first value proposition here is a lower lifetime equipment cost. That comes from the fact that we are now able to use a standardized low-cost technology. Ethernet has been around for decades, and the components for Ethernet does come with a fairly low cost. What also helps on the lifetime cost is the interoperability across manufacturers. That means that more manufacturers can deliver equipment, and that lowers the pricing. Finally, availability of test equipment and tools from other industries will increase, which will also make it easier to use and cheaper to use. Another value proposition is scalability. In a TSN network, it's easy to add additional sensors or other units to the network, and it's also easy to adapt to increasing bandwidth requirements. The right side of this slide all contain value propositions that are related to the convergence of the network, which is one of the key benefits from TSN. The point here is that the same network can be used for both synchronization messages, time-critical information, and all other types of network traffic. First of all, by converging this, you get a reduced and simplified network maintenance, since you only have one network to maintain instead of multiple. Also, the one network that you have uses a standardized technology, which also makes maintenance easier. TSN also inherently includes fault tolerance and redundancy. That includes, for instance, the 802.1 CB feature that I just talked about, which also makes the network architecture more simple. With a converged network, data transparency will also increase. We will no longer have isolated network islands that are difficult to communicate with, but all units will be included on the same network, and therefore the data access will be easy across all the devices. Finally, TSN will bring lower weight, and the reason for that is that the cabling can be reduced because of the converged network. The convergence of networks makes TSN applicable in many different use cases within aerospace, aviation, and defense, since the network can be shared by both time-critical and non-time-critical messages, and also safety-related and non-critical traffic. Networks on aircrafts and satellites are typically divided into domains with specific purposes and requirements. The left part of this slide includes a list of different networks, while the right side includes a graph showing each network requirements regarding determinism and bandwidth. The list here is divided into different types of vehicle. There are three different types. The first type is passenger aircrafts. Passenger aircrafts are typically divided into three different domains. We have the aircraft control domain, which is basically what ensures that the flight happens safely. It includes all the flight control systems like instruments, engine controls, autopilot, crew alert systems, and so on. The aircraft control domain has a high requirements on determinism, since many of these systems require strict synchronization across the network, but the relatively low requirements to bandwidth, since there's not so much data to move around. The next domain here is the passenger information and entertainment service domain, which basically handles all the cabin management. That includes the passenger entertainment, the audio broadcast, the passenger Wi-Fi, light and temperature control, smoke detection, and so on. The passenger information and entertainment system service domain is placed out here with a high requirements to bandwidth, since there could be 500 passengers all streaming video, but the fairly low requirements to determinism. The reason why determinism is not zero is that some traffic is still critical to get through the network, for instance emergency messages and smoke detection alarms. This domain, by the way, also have a high level of security, since there are many unauthorized users on the network, i.e. all the passengers. The third and final domain in a passenger aircraft is the airline information service domain. This domain handles information sharing. This includes weather reports, engine and system performance, flight health management, and so on. The bandwidth requirement is sort of medium in this requirement, since and the determinism is also a bit lower than the aircraft control domain, but still fairly high, since some of the messages may be important and should get through quickly. The next type of vehicle is a military aircraft, which could be both a manned one and an unmanned one. This also includes a flight control system. In military aircraft, this is called the air vehicle system, and this is placed here on the top on the graphs together with the aircraft control domain. Apart from that, it includes a mission control system, which is typically called vehicle mission system. This includes the mission controls, the sensor systems, the video, radar, weapons, and so on. Many of these systems requires a high bandwidth, and it definitely does also include or require a high level of determinism, which is why it's placed here in the graph. The final type of vehicles here is satellite, which also contains a flight control system, platform flight control, placed up here together with the others. And then we have the payload network, which includes the communication transponders, the cameras, the scientific research instruments, and so on, which are the instruments needed for whatever missions the satellite is on. Many of these instruments require a high bandwidth, but the determinism is not that important, since data analysis can happen offline. TSN is applicable in each of these network domains and will bring the value propositions that I just mentioned on the previous slide to each of these. This slide shows a bit more details about the network design in an aircraft. Although an aircraft is chosen in this example, the concepts and considerations are also applicable for other types of vehicles and network domains. The figure includes some of the devices that are typically included in an aircraft. This could be cameras, both indoors and outdoors, various sensors like smoke detection, temperature, vibration sensors, and so on, actuators that actually makes the engines run or the wings turn or something like that, radar system, bridges, a centralized mission control that basically handles everything, and then various processor units that does the data processing from the other units. If we look at the example here, then we have the mission control placed here in the center of the aircraft, and we have the different processor units connected here. Each of the type of devices, for instance the sensors, has their own network and their own processor units. For instance, the sensors are connected here, whereas the cameras are connected in this other network. That means that we have multiple network islands. The sensor network is not connected to the camera network, for instance. The fact that multiple processors are included means that the processors are not efficiently used, since they will at some times they will be waiting for more data from the devices connected. This network structure also includes a lot of parallel cabling, and we will have multiple cables going around the aircraft. And this actually results in hundreds of kilometers of cables in a standard plane. If we then go to a more modern network architecture with TSN, we see here that the mission control is still placed in the center, and then all the other units are placed in a daisy chain that goes around the aircraft. That means that significantly fewer cables are used with this structure, which reduces weight, complexity, and cost for cabling. In this example, the processor units have been combined into a single processor unit that can be time shared by the different devices, which means that the processor units will be more efficiently used than in the other example. The fact that everything is combined into one network gives an easier data access across the network. If there are some devices that does not support TSN, in this example, it's the radar systems. These can be connected using legacy protocols to a gateway that can connect to the TSN network and the mission control. This type of network requires TSN features to function and to make sure that everything is running as it should. As mentioned, the topology shown here is a daisy chain, but it could also other topologies could also be selected, and some of the same advantages would come. I now get to the third part of the agenda, which is a little bit about the TSN portfolio at Comcores. We have a TSN switch called Manticore. This TSN switch is silicon proven at 10 and 25 gigabit per second, and it includes a lot of the TSN features that I talked about previously. The switch can support up to 64 ports with an aggregated switching capacity of 800 gigabit per second. Another example of our TSN products is our TSN MAC, which covers from 10 megabit per second to 100 gigabit per second. This MAC is fully configurable and includes an optional timestamp unit for time synchronization. The MAC also includes several of the TSN features that I mentioned previously. Comcores can deliver on multiple different integration levels and can customize our delivery to your needs. We can deliver both IP cores and software, enabling easy integration in your system. In general, we are open to configure and customize the features in our IP cores so it fits your vertical and your specific needs. We are also open to supply demo platforms so that your integration happens easier and you have something to test on. The different integration levels can be shown here with an example where I've included Manticore here in the center. This is the TSN switch that I mentioned. We can deliver this as a standalone switch in RTL code for ASICs or FPGA. We can also deliver this wrapped with other IPs. So that could include, for instance, the Macs or the PCSs. It could also include a DMA IP that we can integrate and put into a wrapper, which makes integration at your side easier. Finally, we're also able to deliver a full solution, which includes all the IPs shown here, and also a software package that can be run on an internal or external CPU. This slide shows a little bit more about our portfolio. I have here included our chip-to-chip portfolio, where we have IP cores within JESD, Interlaken, and MIPI RFFE. And I've included our Ethernet portfolio, which includes the TSN parts that I mentioned, but also standardized Ethernet IPs here. As you can see, we cover multiple different speeds and also multiple different verticals. I should mention here that our portfolio is, of course, continuously developing, and we have also multiple TSN products under development. That was the last slide that I intended to go through today. So now we have time for some questions, and let me see which ones have come in. There is one here. Which of the TSN features can be used in the asynchronous profile? Yeah, and that's a good question, because some of the TSN features does require a synchronized clock and can therefore not be used in the asynchronous profile. But not all of the features though. Features like QAV, the credit-based shaper, or QBU, the frame preemption, and of course the asynchronous traffic shaping QCR will all function in an asynchronous network. Whereas other features like the time-aware scheduler and the cyclic queuing and forwarding feature will not function without a synchronized clock. Then we have another question here. Would it be possible to connect all devices across all domains in an aircraft to the same network using TSN? In principle, it will be possible. And if you do that, then the TSN features would ensure that the prioritized and time-critical package would arrive with low latency despite of the many different types of traffic that would be on the same network. This is seen as the end goal for aerospace, I would say. But due to safety and security considerations, it may be more attractive here as a first step to keep the domains separated and introduce TSN in each domain to begin with. Which other questions do we have? Here's one. Does the synchronous profile in the TSN aerospace standard includes also asynchronous features? The short answer is yes here. If you comply with the synchronous profile, you will also have the asynchronous parts covered, since the synchronous parts include all the TSN features. Let's see, time is running, but we have time for one more. Can Comcores supply a TSN switch that support 1 gigabit per second? Yes, we can. First of all, then Manticore can support 1 gigabit. It supports more speeds than the two I mentioned. And in general, if you have specific requests, do not hesitate to contact us, as we are open to discuss customization of our IPs and solutions to meet your specific needs. That was it for today. I would like to end by saying thanks a lot for joining and for your interest in Comcores. If you have any questions or requests, you can see the contact details here on this slide, and you're more than welcome to contact us. Have a good day. Bye.